So, what I will do today is basically the uncertainty relation, and and then we will so basically this uncertainty relation. So, once again this covariance matrix gamma, so which is for a n mode state. So, rho is, let us say this is n mode state. So, state of let us say n harmonic oscillators. So, this covariance matrix gamma, it has the entries where j and k runs from 1 to twice n, and then this gamma j k, this is of this form that you take the anticommutator average. So, R j minus R j rho, and then R k minus R k rho with respect to rho. So, this is the, and this R j R k's are basically this is your R vector, which is x 1 p 1 x 2 p 2 x n p n. Okay. So, this you can simplify it, and it turns out to be anticommutator of R j R k minus product of the average values. Okay. So, this is the so this is the components, like this is the position quadrature, momentum quadrature, etc., and these are all in the dimensionless case. Okay. Okay. So, in the case of Gaussian states, n mode Gaussian states, so n mode Gaussian state, its Wigner distribution has to be Gaussian. So, if I take it to be rho, so rho of this thing like x 1 p 1 x 2 p 2 x n p n. So, this is 1 by square root of determinant of this gamma multiplied by exponential of minus half. Now, this is your R, let me see. So, this is R minus average of R transpose gamma inverse, and then R minus average R. Okay. So, what does it mean? This means that take the, this is at the position. So, R is in this case, R is this one x 1 p 1 x 2 p 2 x n p n. These are the scalar quantities. Okay. So, for a n mode Gaussian state, its Wigner function has to be of this form. This is the form, and you see that in order that this is a Gaussian, this gamma has to be positive definite. Okay. Otherwise, this inverse does not. Yes, in order that this is a is a Gaussian Wigner function. So, this is positive definite, right. Now, if I take a classical probability distribution like this n mode classical probability distribution on the phase space, then this is enough to say that look, this is a valid probability distribution. Okay. I mean you can prove that this is normalized everything. So, basically if you take this, do this integral like dx1 dp1 dxn dpn, everything from minus infinity to plus infinity of this w, then this should be equal to 1. Okay. So, this is a normalizable one, and this is indeed a probability distribution. So, for classical probability distribution, as I said, this condition is enough to assure that this is a probability distribution indeed, okay, and this will give you also the marginals. But to say that look, this is a bona fide covariance matrix for a quantum state, n mode quantum state, it needs to satisfy not just this, but something more than that. Okay. And this something more than this is this uncertainty relation. So, which is basically stronger form of Robertson Heisenberg uncertainty relation. Okay. RHUR, and what is the stronger form? Basically, you will have to add the Schrodinger term. So, if I take two observables A and B, so delta of A square with respect to some state rho and delta of B with respect to some same state rho, this should be greater than or equal to 1 upon twice I commutator of A and B with respect to rho square of this. This is the usual uncertainty, and then you will have this term. Okay. So, you can say that this is A minus average of A and B minus average of B square. Okay. So, this is this up to this part, this is usual Robertson Heisenberg uncertainty, and then if you have this term also, then this is basically called Schrodinger term, and this is the Robertson Heisenberg, the stronger version of Robertson Heisenberg uncertainty relation. Okay. So, what follows is that this covariance matrix, I mean not just this is of course true for any covariance matrix. What it satisfies is this one, gamma plus iota by 2 omega, this is greater than equal to 0. And what is this omega? Omega is basically you have the canonical commutation relation. So, this is I sigma y plus I sigma y, this is direct sum I sigma y, I mean for n modes. Okay. So, this is for a one mode, this is second mode, etc. Okay. So, this is a 2n by 2n matrix, and this I sigma y is your 0 1 minus 1 0, this is the 2 by 2 matrix. Okay. So, you have this block diagonal form of this matrix, and this comes from basically your commutation relation, like this R j R k is equal to iota omega j k, for j and k is equal to 1 2 3 up to twice n. Okay. Like x1 x2, that means x1 and p1, that should be equal to iota, x1 and x2 should be equal to 0, all such things will be there. Okay. So, rather than this condition, which is of course true for any covariance matrix, you should have this one. So, this is the condition that if I take a some n mode state, not necessarily Gaussian state, any n mode state, then if I figure out its covariance matrix by this formula, then one can prove that this is satisfied. Okay. So, this I will discuss how to prove this thing. Yes.
Yes. So I have a slightly different understanding of covariance matrix and its positive determinants.
Yes.
So let's say I am dealing with classical random variables, x1, p1, something like that.
Yes.
Then the covariance matrix, yes, I take it to be positive semi-definite, greater than equal to 0. And Heisenberg uncertainty principle gives me that region that you have written gamma plus I omega by 2 greater than equal to I guess.
Yes, yes, yes.
And that implies gamma is greater than. We can remove the equal to sign.
No, see the thing is this gamma inverse, it will not be defined if I take positive semi definite. That means, if it has got at least one eigenvalue 0, then gamma inverse is not defined. Okay.
Okay.
Okay. So, that is why, I mean, that is a trivial case. So, that is why I need to consider this gamma to be strictly positive. It has to be positive semi definite, no question about that, but you will have to take it strictly positive definite, otherwise gamma inverse will not exist.
Okay, thank you, sir.
Okay, yeah. Okay. So, now what one can prove, as I said last time, so this is a necessary condition for n mode state. I mean, basically this is any n mode state, for any n mode state this condition has to be satisfied, and this is basically, this is actually the uncertainty relation. No. As I said, this is true irrespective of whether your state has Wigner distribution Gaussian or not, okay, for any state. Okay. But for Gaussian state, what one can prove is that this is also sufficient, in the sense that if I provide you some gamma which is positive definite, okay, if I provide you some gamma which is positive definite, and if it satisfies this condition. So, this is a 2n by 2n positive definite real matrix actually, and if it satisfies this condition, then one can come up with a state, n mode state, which is a n mode Gaussian state, for which this gamma is the covariance matrix, right. So, this is for Gaussian state, this is both way true, that means this is necessary and sufficient condition for Gaussian state. Okay. In the sense that if I provide you a 2n by 2n real symmetric positive definite matrix satisfying this condition, then you can find out n mode Gaussian state having this as covariance matrix. Okay. And therefore, of course, this would be satisfied, no doubt of it. But for general state, which is not necessarily Gaussian state, I cannot say this thing.
For general state, this cannot be. I mean,
this is satisfied for general state. But if I provide you, okay, so maybe I will use another notation. Let us say this is a 2n by 2n real symmetric positive definite matrix satisfying this condition. Can I associate the, can I say that this is a bona fide covariance matrix of some n mode state? Okay. So, if I ask that question, the answer is generally no. But if you know beforehand that the state is Gaussian, then of course you can do that. Yes. Okay.
So, I just want to.
Yeah, sure.
So, given gamma, we can find omega. Is that the other?
No. Omega is this omega.
Omega is defined.
Yeah. This is so. Given n mode state rho, this is your covariance matrix, and that will always satisfy this condition.
For any like
For any n mode state, its covariance matrix must satisfy this condition.
regardless of what the distribution looks
What
like.
is the phase space distribution function is. Okay, but the question now is opposite, because this is a positive definite matrix, real matrix, positive definite real matrix. So, let us say somebody has given me a 2n by 2n positive definite real matrix, let us call it as gamma tilde, okay, which also satisfies this condition. That means gamma tilde plus iota by 2 omega greater than equal to 0.
Then you can always write a Gaussian distribution.
Exactly. I can always find a Gaussian state whose covariance matrix is this.
And omega is given to us to be this thing.
Yeah, omega is this, this is the structure of your phase space. This is the canonical structure. Okay.
But why this choice of omega?
No, see, this is what this omega is this coefficient matrix.
Okay.
Okay. Why this comes here? I'll go through that. Okay. Why this particular comes here? Okay. So let me now go through it step by step. Okay.
And my guess is that you'll try to derive this using the strong form of uncertainty.
Yes. So, as I said that for a classical probability distribution, n mode classical, that means I mean 2n dimensional phase space, there gamma positivity of gamma is enough. Okay. In fact, if I provide you this gamma positive definite real symmetric gamma, then of course you can figure out a corresponding probability distribution for that. That is not an issue. But for quantum case, you will have to also have this condition, satisfy this condition, because of simply the uncertainty. Okay. Right. So, let us take first the single mode case.
If we use equality, uncertainty equality,
Mm.
then this relation will be modified, right? According.
Yes, of course. Yeah. This is the one.
Okay, then something new can
But
come out.
but it may come up, but you will have to be careful that it has to be state independent. Okay.
Okay. I see.
Okay.
And in this, like, this uncertainty relation that we have written down, it's like if you choose A to be the momenta and B to be the positions, then I guess this first term is the same as omega and the second term is same as gamma, the covariance. Like the second term is the covariance.
No, I didn't get what is your point?
So in this uncertainty relation, if A were the position and B
And
were
this is the moment.
momenta,
Yes.
then this thing, like the first term of the uncertainty of the right hand side of the uncertainty, that is like omega squared or something.
Yes.
And the second term is gamma squared.
It should be. Yes. So let me see. Okay. Okay. So this is single mode case. So single mode case. So I have a state rho which is single mode state. So let me look at the gamma matrix. What is it? This is what is gamma 1 1? Basically, it is x square rho minus x rho square. So this is half xp plus px rho minus x rho p rho. This is half xp plus px rho minus x rho p rho, and this is p square rho minus p rho square. Do you agree? Right? This is the thing. Okay, good. So, this is your gamma. So, of course, you can prove that this is positive definite, it is not at all a problem, right. So, now if I look at the stronger form of uncertainty relation, what, how in terms of, so let us take A is equal to x and B is equal to P. So, this will become basically x square rho minus x rho square into p square rho minus p rho square. This is the first term, and let us take this on this side. Okay. So, minus what will be this? So, this is basically what I have written there, right. So, this is half x p plus p x rho minus x rho p rho square. Do you agree with me? This one, and I have taken this one. So, this is greater than or equal to, what about this one? This is iota. So, this is basically 1 by 4, right. Now, what is this condition? If I look at this, this basically tells you that determinant of gamma is greater than or equal to 1 by 4, right. Okay. And which has to be the case, I mean has to be the case means, of course, if gamma is a positive definite matrix, then all its eigenvalues are positive. So, therefore, determinant of gamma has to be positive, no doubt of it, but this tells you that this is not just positive, it is greater than or equal to 1 by 4. Okay. Right. Is this fine? So, now, so therefore, the uncertainty relation, the stronger version of uncertainty relation for this case, for the single mode case, boils down to this one. Okay. So, now let us take this, with this gamma, let us take 1 by iota omega. What is your omega here? So, remember omega is again a 2 by 2 matrix, right, for this case. So, this is 0, of course, you know this is usually this is 1, this is minus 1, this is 0, right, if you look at that. So, therefore, if I look at this, this is, you know, I am not going to write here again. So, this plus iota by 2 omega, what happens is this plus iota by 2 and this minus iota by 2, right. Okay. And now, positive semi definiteness of this means what? I mean, of course, this is a, so this means that because this trace is, you know, this trace is basically non negative, right, because this is trace is the sum of these two diagonal values is non negative, right. So, the positive semi definiteness will be determined by the signature of determinant, right. Okay. It will be determined by the signature of this determinant. So, if I can prove that this is greater than or equal to 0, then this tells me that this is positive semi definite. Is that correct? Because trace is non negative and determinant is non negative, means the matrix has to be positive semi definite. Okay. It is only true for 2 plus 2. Yes, yes. So, now what is this condition? If you look at this, so what will be the change here? And I am not going to write everything again. So, the only change if you look at
In the last term, that will also give you 1 by 4.
What did Anupam say? This is only true for what?
no, this is only true for 2 by 2. Well, it is true in general, but for general case you will have to prove it separately. The only this condition will not be enough. Okay.
No, I am saying that for 2 plus 2 matrix only
This is true, but for higher dimension
you need another
other conditions. Exactly, exactly. Okay. Now, what about this determinant? Can you tell me? So, this means that I do not want to write, but still I will have to write, I guess.
you have the first term is anyway
Yes.
term only I by 4 will 1 by 4 will come. So anyway it's greater than 0. Everything is fine.
So,
Here will be 1.
no, is it okay? Minus 1 by 4 or plus? This is plus.
Plus 1 by 4, sorry. Plus I by 2 and minus I by 2.
But
Yes.
overall minus sign in the determinant on that. But
Yeah,
This I think this is correct.
that would be the determinant.
Yes, that is the determinant. Okay. So, the determinant basically this tells you that determinant of gamma plus I by 2 omega greater than equal to 0 means this. Okay, right? And that is automatically satisfied. This is the stronger version of the uncertainty relation. Okay. So,
Now I am little bit confused. Is it not a circular argument?
why? This I did not prove it, I just stated it. So, for single mode case, I am proving this.
Oh, but your assumptions is the stronger uncertainty.
That is anyway true for quantum theory, right?
But I don't know the second term.
Second term is also true. This is always true for any quantum state and any bona fide observables. This is always true. The stronger version of Robertson Heisenberg uncertainty. This is always true. Okay, in quantum theory.
Then you are using these to prove that determinant. Okay, I see. Yeah. That means single mode case, it validates.
So,
It is valid.
so where from you get the confirmation about this? You are getting confirmation about this from this uncertainty relation. Okay.
Got it. Next, not sorry.
Okay, good. So, therefore, at least for single mode case, we managed to prove that this is true. Okay, good.
So earlier this condition gamma plus I by 2 omega greater than or equal to 0. That was not a follow up from the stronger version of the Robertson Heisenberg uncertainty relation. It was a conjecture kind of thing.
No, it is not conjecture. I said that this is going to be true. I did not prove it. I proved it only for single mode case.
Okay.
And this is a consequence of the stronger version of uncertainty.
So how do you prove considering many initial steps? Or
Which
something?
did I prove?
This-
The uncertainty relation.
No. This condition.
No, he did not prove. He just gave.
No. If you want to prove it, then how do you prove? I mean,
What is your
No,
question?
he's saying that is there any general constructive proof of this statement?
Which
this-
statement?
This gamma
This Gaussian
plus I.
necessary and sufficient condition.
This is not necessary and sufficient for generic state. As I said, this is a necessary condition for generic state. Okay.
Right. For Gaussian state, you said
It
this
is necessary and sufficient.
right?
Yes.
Yeah.
So, I have not yet proved anything
Right.
regarding this inequality. Only thing I have proved is that this inequality is valid for any single mode state.
Single mode.
Yeah.
No. I mean, I got your point. I am saying that if you want to prove that equation, inequality, how do you prove? I mean,
Well, okay. Okay, so there are several. I mean, there are different ways. So the way which I like most is a canonical way. So canonical way means that you go to a minimal form of your state.
Minimal form.
Yes, in the sense that you forget about extra things in your state which are not necessary to prove this state. Okay, so what are those extra things? I'll talk about that. So you go to a minimal form of the state, so that you will not lose any generality about the state. Generality in the sense of proving this answer, this inequality. So you go to a canonical form, and how do you go to canonical form? You will have to do similarity transformation, I mean unitary transformation kind of thing, to go to a canonical form. And once you have a canonical form, proving that will be much easier.
Okay.
Okay, so that is the idea. It's like coupled harmonic oscillator. Let's say you have coupling there, quadratic coupling, which depends upon the distance of the positions. How do you prove that? I mean that how do you get the energy eigenstates and eigenvalues? You go to a normal form, and basically then you can cast it as uncoupled harmonic oscillators. So similar thing here. What you can do is you can cast every n mode state to a canonical form, which means a bunch of thermals. I mean basically is a tensor product of thermal states. Okay, single mode thermal states. And once you prove uncertainty relation for each such single mode thermal states, uncoupled, they are all uncoupled, then you can prove this thing also. Okay, so that is the idea. Of course, you cannot use that transition from your original state to these canonical form, namely thermostat, every time. For example, if you want to deal with entanglement, you cannot do that. But here it is uncertainty, so you can do anything global allowed.
So that similarity transformation globally you can do that.
Yes. Okay.
Does that take us to the direct sum or the tensor product?
This is I have written direct sum because it is a block diagram.
Yes, yes. But
Okay, so actually it is a tensor product of in this way it is a tensor product of n single modes, Hilbert spaces. So Hilbert space wise it is, see what is this? This is a 2n by 2n matrix, right?
yes.
So this looks like basically this 0 1 minus 1 0, then so this is what is that 0 1 minus 1 0, so something like this.
But this is like mathematically a direct sum.
This is not tensor product, that is this is not tensor product, is fine, but the Hilbert space, the entire Hilbert space is the Hilbert space of n oscillators.
Yes, but that's also I think mathematically a direct sum rather than a tensor product. I'm not sure.
Mathematically, what is
Mathematically a direct sum rather than a tensor product.
What?
it's a direct sum. Yeah.
Which one?
This meant
No, that's
I
what
mean,
you have
if
written.
you have like if you have uncoupled harmonic oscillators,
Then it
and
would be
a-
tensor product.
Yeah.
See, this is just a notation, I could have written this entire matrix form. This is
I just get confused between these two actually, whether like, mathematically it's appropriate to use direct.
no,
form.
this is an operator acting on the entire n mode Hilbert space.
Yes, and the dimension of the Hilbert space is 2n. Like
No, don't dimension, I mean phase space is 2n. Yes, phase space is 2n.
I think it is very evident if you look at the covariance matrix,
Yeah.
because like the next identity, that omega is actually RJ RK kind of thing.
Yes.
So then
So that is a direct sum structure.
Yeah,
That's not a
direct sum
tensor
structure.
product.
That's not a structure. Direct sum structure.
So in the here covariance matrix, omega, these are all matrices.
Yes.
Okay, and these are finite dimensional matrices, basically 2n by 2n matrices.
Yeah, but like if it's were a tensor product of let us say like two dimensional spaces, then it will be 2 to the power n rather than 2n.
Exactly,
Yeah.
exactly. No, I am not doing that. Yeah.
No, but he is doing in the fog basis.
Sorry?
You are using fog basis literally, in some sense.
I mean, in this case,
I am using
You are
fog
not-
basis. You know,
you
I
are
am
not
using
the
fog.
proper Hilbert
Okay, so
space.
let's see. I am using fog basis.
Yeah.
But when I talk about these matrices, okay, these are finite dimensional matrices,
yeah,
2n by 2n matrices.
That is true. That is true. Yeah, yeah. The finite dimension analog of the fog basis I am trying to say. Something.
It is not yet analog. You know, so these does not capture everything about n mode state. So n mode state is still acting on tensor product of n single mode Hilbert spaces. Okay.
Okay, and this is just like
Okay,
something
okay.
we isolated.
So
Yes, yes.
infinite dimensional position momentum operators are kept in such a way that they
So
form a
this is
matrix to-
actually, you know, like single mode case.
Yeah.
In the single mode case, I still know my Fock space is infinite dimension,
That is true. Actually.
right? But this matrix is 2 by 2 matrix.
Yes.
The omega is 2 by 2 matrix.
Yes.
Okay. Of course, this will not capture everything about the state.
So at the level of gamma and like covariance matrix and this omega matrix, it's like a
It's a
direction.
finite dimensional system. Yes.
In the level of XNP, it's like a tensor. Something.
Exactly. Exactly. Yes.
just for mathematical to reduce the mathematical complication, it is useful, right?
No.
It is definitely useful. But once again, I must repeat that this does not capture everything about your n mode state.
But for Gaussian state, it is enough.
For Gaussian state, this is
Surprising.
yes.
It's not surprising because Gaussian is completely defined by the mean and
Yes,
mean.
I mean defined by the first and second order moments.
Yes, yes.
So therefore,
Yeah.
It's like
In some sense, yeah. That is true.
in other
Still-
distributions, you need all the other moments also to do.
That is
exactly.
true. If you think in terms of probability distribution, I'm trying to think of like,
Even in probability distribution also,
yeah.
you know, you can have Gaussian probability distribution which will be characterized by only first and second order moments.
Right.
But if you go to any other probability distribution, you cannot have this property. So there, every higher order probability distribution will be, every higher order moments will be non-zero.
Yeah, if you'll think in terms of probability distribution, but if I'll think in terms of like harmonic oscillator, let's say vibrations or something like that, then I get confused because it's like, I don't know, I cannot make you understand what is my uncanny things about this. But there are something uncanny about this for me. Like why Gaussian state, I understand there is only covariance and things are important. But this omega does not capture so much of information into the state, but still for Gaussian it is enough.
Omega and gamma. Omega is of course, you know, it's a structure,
This is just a
structure matrix
Yeah,
you can
exactly.
think of. But gamma,
Gamma.
so gamma can capture everything about Gaussian.
Yeah, that is true. I mean, yeah, I understand, but okay.
Omega captures like the commutation relation between any.
Any quadrature, right?
Yes. Yeah, I mean, so this is, you know, I would say it's a blessings for us. You know.
Yeah, in some sense, yeah. True.
Okay. So, okay. So, there is this theorem which I am not going to prove because this is a man. So, this is called Williamson's theorem. I think this is something during 1920s, you know, that was proved. It tells you that if gamma, okay, yeah, so if gamma is the covariance matrix of an n mode state, right?
Theorem definitely did not state N mod state, right? What did it? I mean, like 1920s.
Well, I mean, that's okay, you know.
Yes, yeah,
I mean, 2n dimensional phase space you can,
okay.
okay. Then there always exists a canonical transformation. Well, it's a linear canonical transformation. I mean, linear canonical means this condition has to be satisfied. Okay, canonical transformation. So, which is basically R going to S of R. So, S is a 2n by 2n matrix. Okay, canonical transformation this such that S gamma S transpose, or you can have S transpose gamma S, whatever be the case. This is in this form diagonal kappa 1, then kappa 2, kappa n. Okay. Sorry, I mean, you may think that this is k, this is kappa. Okay. And all these will satisfy that this kappa j is greater than equal to half for j is equal to 1, 2, 3 up to n. Right. So, this is again a 2n by 2n matrix, diagonal matrix. So, you can cast every covariance matrix, yes, every covariance matrix under this linear canonical transformation in this diagonal form.
What are the elements of the diagonal matrix?
Kappa 1, kappa 2, kappa 2.
There is no restriction other than greater than half or half.
So, because this is the uncertainty, you know, this is basically the uncertainty, and this is the uncertainty relation, you know, that we spoke about. I'll talk about this now, you know, that this is exactly the uncertainty relation for the single mode case. Okay. Eventually, you know, it is in the single mode, right? This one, all this in the single mode case.
Significance of this.
So, basically this is, you know, this is just n mode thermal state with temperatures not kappa, something related to kappas. So, this is single mode thermal state with temperature associated with kappa 1, single mode thermal state temperature associated with kappa 2, so on and so forth.
So the diagonal elements are the thermal state.
Yes. So, this will be I'll show you that this in the single mode case this corresponds to diagonal of K1 kappa 1 corresponds to a thermal state.
Sir, I mean, in the gamma, there were actually variants in X1 and P1 and all, no?
Yes, right. The one which I have written is gamma jk. Okay.
It is surprising for me in two ways. One thing is like it feels like analogous to the spectral decomposition what we do in the finite dimension case. No? There is a similarity transformation which also makes the n mode state description into a diagonal form. But that is not a big issue. For me, the big issue is that
I mean, these are not spectral, these are not eigenvalues
I understand.
because this is not unitary. Okay.
Yeah, something analogous. But anyway, that is not my point. My point is it's something.
But initially, those variants will be different, right? If you start with a gamma, I mean, variants for the X and P will be different, right? After doing this transformation, it will be
All of them will become same. Okay. And this off diagonal terms will vanish.
Vanish.
Yes.
So, Professor Ghosh,
Yes.
so does that mean that this transformation basically converts a pure state into a mixed state with just or no diagonal or no off diagonal entries, something like that? The correlations, the cross
Well,
correlations vanish.
for a pure state it should remain pure state, because this corresponds to a unitary transformation, this is. So, in that case of course, we will have to choose this kappa such that it will be 0 temperature.
Oh, okay.
So, it will pure state will go to pure state, mixed state will go to mixed state, because this is unitary transformation. Okay.
Yeah, thank you, Professor Ghosh.
Sorry, I
Yeah.
did not listen. What are those kappas here? And the condition kappa j should be greater than equal to half.
Yeah. So, this is I will give examples, because I am not going to prove this theorem, this is much more complicated. I will give example how to get this thing, okay. But essentially this tells you that if you start from a generic n mode state and you apply and you get the you figure out this covariance matrix, which will of course satisfy the uncertainty, and now you apply unitary transformation corresponding to this linear canonical transformation, which can be rotation, displacement, squeezing, whatever you want to call it, okay. And not even within that group, okay, it can be anything. Then what you can prove is that there exists at least one such canonical transformation, which will bring the covariance matrix in this diagonal form.
And this kappa greater than equal to half comes from the.
This is the this I will show that this is the uncertainty.
Okay. Sure.
For me, the surprising part is it's like its emergence in 1920s. How is it possible to get a theorem like this in 1920s?
No, probably the original.
This is a mathematical like this?
The original statement is not like this, of course.
The original statement is probably that kappa j is greater than the commutator of the two operators, because like this is like 1 by 2 times 1 iota by 2 commutator of x and b, right?
I see.
So that is probably like for two operators.
Okay.
Maybe that
There
is
might
the-
be,
yes.
but still it's like.
Adapted like this is the proof
I
adapted to
understand,
the
yeah.
quantum case.
Yes. I mean at that time of course nobody. So, people used to call this canonical commutation relation or CCR algebra or something like that.
Before Heisenberg uncertainty, it was already there in the literature. People did not
Yes,
give
yes,
enough
yes,
attention.
Maybe during same time, okay.
Okay.
Probably they did not know what operators to find the uncertainty between. Just for
Yes.
any two operators, they proved this theorem.
Exactly.
Yeah.
Yeah, that is true. They did not have physical observable to talk about.
Yeah.
See.
Okay.
So math existed.
No, this is true. If you look at math literature, there will be plenty of such
Yeah,
results.
exactly.
General relativity, the math existed before the general
Exactly.
relativity to a physical context.
Yes.
Nobody listened to him. That is his only problem.
Okay. So, let me, yes.
Just like the dates, I would just like to speak about the date. There is a paper by J. Williamson in American Journal of Mathematics in 1936.
Oh, this is 1936. I thought it is 1926. Okay.
Yeah, I can see that in that Pramana review, symplectic.
Okay. 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 So,
What is the journal name?
American Journal.
what is this journal?
American Journal of Mathematics.
Yeah, it's
American
prestigious.
Journal.
But 1936 means okay, still.
You are satisfied.
I am
Okay.
satisfied.
yes.
I am satisfied. No one thought about uncertainty before Heisenberg. That's what I have to prove.
So, this is a correct 1930. Okay.
Okay.
Right. Okay.
36 actually, 36.
So, actually it should be 36. Yeah?
36.
What is that? American
Journal of Mathematics.
Journal of Mathematics.
Journal of Mathematics. I don't even, the American Journal of Mathematics is still there. I guess.
Yeah, it's very prestigious.
Okay, good.
American Journal of Physics. That is for the students, college students. That's
So, let us take single mode
So,
thermostat.
Gosha,
Yes,
can I seek a small clarification?
yes.
So once we have the covariance matrix, we pretty much know everything, right, about that particular state. So this
No,
Williamson
no,
theorem-
no, a little bit addition. So, you know everything about this state provided it is a Gaussian state.
Okay. So this Williamson's theorem, doing a canonical transformation and getting a diagonal form, what does it provide us any additional insight to?
So, basically if you guarantee that this S, this canonical transformation corresponds to a Gaussianity preserving transformation, okay, like squeezing or displacement etc., then of course, your original state has to be Gaussian, because this is Gaussian, thermostat is a Gaussian state.
Yes.
But had it not be the case, not been the case, then of course, you can have any canonical transformation. It can have even higher order, it can be generated by higher order Hamiltonians also, okay, not just quadratic one.
Okay. Thank you, Professor.
Okay. So, let us consider this single mode thermostat, which is rho thermal is equal to e to the power minus beta. Well, I should have taken this harmonic oscillator Hamiltonian, but you know that this is fine if I take this trace of e to the power minus beta a dagger a. See, originally the harmonic oscillator Hamiltonian looks like h cut omega a dagger a plus half, and then you should have basically it should be like h cut omega by k b t, right, this coefficient. But you can take h cut omega k b everything 1. So, this is inverse temperature, okay, this beta. So, this is your sum over n is equal to 0 to infinity e to the power minus beta n, this is n n, and this is sum over m is equal to 0 to infinity e to the power minus beta m, and this is equal to so this part will be what 1 upon, so basically this is 1 minus e to the power minus beta, then sum over n is equal to 0 to infinity, this is e to the power minus beta n n n, right. This is your thermostat, and now you can talk about the average photon number. So, average occupation or whatever you call occupation number or average photon number. So, which is n, this is what I will use this notation. So, this is basically trace of rho thermal with a dagger a, okay, and therefore, this will be what will be this?
But I think summation you have written as 1 minus e to the power minus beta.
That's geometry.
That should be not to the power minus 1. 1 minus x to the power minus 1. It should not come to the denominator.
Denominator thing only he applied geometry.
Oh no. Okay, this went up. Okay.
So, this is basically sum over 0 to infinity n rho thermal n, okay. So, basically this will be 1 minus e to the power minus beta, then n is equal to 0 to infinity n, and then e to the power minus beta n, right. And what will be this? This is your sorry,
It's called the
arithmetic geometry progression. So, yeah, so this is d d beta of Yes. So, is this correct?
Yeah.
Yes.
And this will be therefore 1 minus e to the power minus beta, here is minus, and then d d beta of 1 by 1 minus e to the power minus beta. So, this is e to the power minus beta by 1 minus e to the power minus beta. So, basically 1 by e to the power beta minus 1. Okay. So, this is n bar, n hat. So, therefore, you can. So, I want to express in terms of this n average. So, basically e to the power beta should be equal to 1 plus 1 by average, right? Is that correct? Yeah. So, this is n by n plus 1. So, this I can write as 1. No, is that correct? Minus beta. Yeah. No, then there is a problem. Is minus sign. Where is this minus sign coming?
That you have done correctly.
So there's a minus sign inside the del over del beta.
Yeah, but if you
Minus-
take this, you minus sign will go away, right?
Okay, you brought it up.
Oh no, no. You missed another minus sign. See, it is 1 minus e to the power minus beta to the power minus 1. For that 1 minus, and it is 1 minus e to the power minus beta.
Okay.
So 1 minus x you are differentiating, right? E to the
Yeah.
power minus beta also have a minus sign.
But is this not correct?
No, this is not correct. There should be a minus sign.
There is a mistake.
Minus sign.
Then how can
There
it
should
be
be a
negative the number of particles?
Average
There is-
number, how can it
So
be
this is
negative?
like d dx, so 1 by 1 minus x, right?
No, just the question. The final expression e to the power beta minus 1 is positive, right? So average n is positive. But if the sign were opposite, then this will be negative, right? Like average
Yeah.
n
Yeah,
can't
that
be
is true
negative.
actually. Yeah. This must be true. Okay.
Oh, no, sorry.
Should be n plus
This is,
1 plus.
see, this is the problem.
Right.
Okay.
This is the post observation I should have.
Yeah.
Yeah.
Okay. So, e to the power beta, so e to the power minus beta is, sorry. Yeah. Yeah, things should be consistent, okay. And then e to the power beta is n by n plus 1 whole to the power n. So, this is actually 1 by average plus 1. Yeah. So, this is fine. This is your thermal state, right. Okay. Now, so what I want is, maybe I will erase this part. So, I will just write for you e to the power beta is equal to n plus 1 by n. So, now what I would like to get is the covariance matrix of this. Okay. So, look at here, this is Fock state, occupation number state. For any occupation number state, I mean basically this one, the average of position and average of momentum, it should be 0, right. This is always the case, right. Right. So, and what about n x square n? So, x you know I can write it as half n a square plus a dagger square plus twice a dagger a plus 1 n, right. I mean, yeah. So, this will be, yeah. So, this will be n plus half, right. Same is the case with p square, right. So, if I now do this thing, x square rho thermal minus x rho thermal square, this is anyway 0, right, because for each of them it is 0 and therefore, the sum will be 0. So, this is n plus half and same is the case with p square rho thermal minus p rho thermal square, right, n plus half.
There should be sum over that coefficient. I mean, we are calculating average with respect to the thermal.
Sorry. Yeah, correct. Yes. This is not true. I mean, this is for n only. Sorry. This is for n only. Yeah. Right. This is for this state. So, therefore, x square, yeah, I will have to do this rho thermal. What will be this? This is 1 by n plus half sum over n is equal to 0 to infinity. This is n by n plus 1 to the power n plus half, right. Okay. Yeah, because for this you will have n plus 1 plus 1. Okay. Okay. Now, this the first term is again if you remember, this is basically the average n, right, with this one. This is the average n, right, and plus, and this is just your probability. So, this is half.
What?
Yeah, this half, because this is basically a probability distribution, right. So, add up to 1. So, half multiplied by sum of your probabilities, which is 1. So, 1 into half is half, right.
No, but my point is how the expectation of n came out and such. Okay. This is a probability distribution, and you are taking expectation value of n.
Yeah, because this n times this is the average n, right. I mean the average photon number. Okay. And this is same as p square rho thermal. Okay. So, fine. So, and now you will have to look for this one, half xp plus px rho thermal minus x rho thermal p rho thermal. Now, this anyway it is 0 and 0, right. So, I will have to look for this, and this is your basically iota by 2 a dagger square minus a square rho thermal. Okay. And so, I can take this iota by 2 outside. So, I will have to take a dagger square average with respect to rho thermal, a square average with respect to rho thermal. So, if you do all this, what you will see is that this is 0. Okay. So, this you can verify, this is simple, this you can put it here and you get it, this is 0. Okay. So, therefore, if I look at the covariance matrix, this case it is n plus half 0 0 average n plus half, right. Okay. This is the covariance matrix. Now, if we look at that, average n can never be negative, average photon number can never be negative. So, therefore, this is always greater than equal to half, this is also always greater than equal to half. So, if I call it as kappa, this is also kappa, then it tells you that kappa has to be greater than equal to half, and this is nothing but the uncertainty relation that I mentioned plus iota by 2 omega. If you calculate this, you will have here, I think, yeah. So, what will you have here? This is, I think, iota by 2, this is minus iota by 2, and now if you take the determinant, this is the condition that you will get. Determinant of this has to be greater than equal to 0, which is same as the uncertainty relation, right. So, for single mode thermostat, you see the I mean the covariance matrix must be of this form, where this kappa or this n hat. So, basically this is equivalent to saying that the average value is greater than equal to 0, which is anyway true. Okay. Right. Clear?
For thermostat, you don't need any canonical transformation. Practically, this is the identity.
Yes. Yes. So, now if I pose the in reverse question, hey, what is the time now? Okay, so if I pose the reverse question, that let us say somebody has given me, so let me pose this question, that gamma tilde is equal to this kappa 0 0 kappa, okay, where kappa is greater than equal to half. So, this is a real symmetric and positive definite matrix. Okay. Can I say that this corresponds to covariance matrix of a bona fide single mode Gaussian state? Yes, I can, because given this kappa, I know what is the average photon number, and then I construct the thermostat with that average photon number. Yes, yes. Okay.
For single mode, this is true. For
higher mode also this is true. So, that is what I am going to do later.
Okay.
But for single mode, so therefore, you see that once you have this covariance matrix satisfying this condition, you can get a single mode Gaussian state having this as the covariance matrix. Well, for the restricted case of Gaussian thermostat, but then we can generalize it, okay, for any Gaussian state.
As you say, we can make a canonical transformation to make the Gaussian state as a
Yes.
collection of.
And now, any two Gaussian states can be connected through a canonical transformation, which is realized by a quadratic Hamiltonian, and that is a Gaussianity preserving transformation. And therefore, from such a thermostat I can go to any single mode Gaussian state.
True.
So, as a result, basically it tells you that in the question of uncertainty relation, okay, it is enough to for Gaussian state, of course, it is enough to look at the thermostat, and we will see that this is indeed true even for more than single mode.